In July 2025, one of the most powerful earthquakes in modern history tore open the seafloor off the coast of Russia. It measured magnitude 8. 8. That makes it the sixth largest earthquake ever recorded by modern seismic instruments anywhere on Earth, and the largest earthquake anywhere on the planet since Japan's catastrophic Tohoku earthquake in 2011. People who study earthquakes for a living, people who spend their careers reading seismograms and analyzing fault ruptures, described it as a once-in-a-generation event. The rupture propagated along the Kamchatka subduction zone for approximately 390 to 600 kilometers, lasting roughly 4.5 minutes. 4.5 minutes of continuous rupture. The ground along the Kamchatka Peninsula shifted by up to 2 meters to the southeast. A trans-Pacific tsunami was generated. Waves were measured at a run-up height of 33 meters in one narrow coastal valley near Vesnik Bay. That is higher than a 10-story building, produced by a single wave of ocean water arriving after the rupture. 7 volcanoes on the Kamchatka Peninsula erupted simultaneously in the days following the earthquake, something that had not been seen in that region in nearly 300 years. One of those volcanoes, Krasheninnikov, erupted for the first recorded time in all of human history, 4 days after the earthquake struck. All of that is extraordinary. All of that is the kind of thing that belongs in every geology textbook published from this point forward. But it is not what this video is about. This video is about something quieter and stranger, and in its own way, more unsettling than any of those things. It is about what scientists announced just 2 days ago, on April 17, 2026, at the annual meeting of the Seismological Society of America. It is about what a researcher named Eric Bose, an associate research scientist at the Lamont Doherty Earth Observatory in New York, found when he went looking through the earthquake records for eastern North America in the months after the Kamchatka rupture. He found earthquakes. Tiny ones, mostly around magnitude 2, the kind that instruments detect, but people generally do not feel. But they were there, in places that had been seismically quiet before the Russian earthquake struck. And they were not random. 3 separate earthquake sequences in 3 American states, Pennsylvania, New Jersey, and Massachusetts, all began in the hours and days and weeks after that magnitude 8. 8, rupture on the other side of the world. Bose and his colleagues are now reporting that those American earthquakes were triggered by the Kamchatka earthquake, not by the tsunami, not by anything that moved through the air or the water or along any road. By the seismic waves themselves, invisible pulses of energy that traveled through the body of the Earth, crossing thousands of miles of rock and ocean floor, and arriving underneath Pennsylvania and New Jersey and Massachusetts with enough force to start breaking things. A single earthquake in Russia broke the ground in 3 American states. And almost nobody knows it happened. Before we get into the science of how this is even possible, let me tell you about the earthquake itself, because the Kamchatka event is one of the most remarkable seismic stories in recent decades, and it deserves to be understood clearly. The Kamchatka Peninsula is a long finger of land extending southward from the Russian Far East into the North Pacific Ocean. It sits directly above one of the most geologically violent subduction zones on the planet, the Kuril-Kamchatka Trench, where the Pacific Plate plunges beneath the Okhotsk Plate at a convergence rate of roughly 76 to 90 millimeters per year. This is fast by geological standards, and it produces earthquakes with a regularity that makes Kamchatka one of the most seismically active places on Earth. The region has a history going back through centuries, a magnitude 9. 0 earthquakes struck almost exactly the same area in 1952, generating a tsunami that caused destruction across the Kamchatka coast and the Kuril Islands. The 2025 earthquake did not come without warning signs, though the warning signs were subtle and were only recognized in retrospect. In the 10 days before the magnitude 8 main shock, the region was struck by 50 earthquakes of magnitude 5, 0 or larger, including a magnitude 7, 4 shock on July 20th. Researchers who later analyzed the 4-shock sequence found that the magnitude 7 event had brought the fault patch where the main shock would eventually nucleate approximately 5 bars closer to failure. In earthquake terms, that is a very large stress change. The fault was being loaded, the pressure was building, and then on July 29th, 2025, at 11:24 in the morning local time, the main shock arrived. The fault ruptured along a segment that overlapped almost precisely with the 1952 rupture zone, re-rupturing ground that had broken more than 70 years earlier. The rupture lasted 4.5 minutes and produced slip of up to 30 to 40 meters on some patches of the fault. The rock on one side of the fault moved 3 to 4 times the height of a person relative to the rock on the other side in a matter of minutes, kilometers beneath the ocean floor. The tsunami that followed was real and dangerous, but it was weaker than models initially suggested it might be, which is one of the remarkable aspects of this earthquake. Despite the extraordinary magnitude, the destructive tsunami that many feared did not fully materialize in distant locations. Hawaii received waves of up to about 5 feet. California recorded waves of about 1, 6 feet above tide level at some gauges. There were evacuations across Japan, Hawaii, Alaska, and the west coast of the United States. In Japan, one person died indirectly as a result of tsunami-related evacuations, and 21 people were injured. In Kamchatka and the Coral Islands, close to the epicenter, the waves were genuinely severe, up to 6 meters in some locations, flooding coastal towns and causing significant damage. But the catastrophic Pacific-wide tsunami that the earthquake's magnitude seemed to promise did not arrive. It was, in the words of one scientific report, the largest earthquake to not cause any casualties through ground shaking or its tsunami. Seismologists will be studying why the tsunami was weaker than expected for years. Meanwhile, something else was happening that no one was watching for. Eric Beausset was in the middle of tuning parts of his earthquake detection workflow when the Kamchatka earthquake struck. His work focuses on what seismologists call stable continental regions, places like the eastern United States, where there are no active plate boundaries nearby, no obvious tectonic forces driving deformation, and yet where earthquakes happen anyway, persistently, in ways that the standard models of seismicity struggle to explain. Why does the ground move in Pennsylvania? Why does New Jersey have earthquakes? Why does Massachusetts, sitting in the middle of one of the geologically oldest and most stable pieces of crust in North America, produce tremors? These are genuine scientific questions without fully satisfying answers, and Beausset's work is part of the long effort to find them. After Kamchatka ruptured, he decided to look. He went through the Eastern North America Earthquake Catalog, the continuous record of every detected seismic event in the region, and searched for any change in seismicity after July 2025. What he found was not nothing. 3 earthquake sequences in 3 different states, all showing a clear signal of being connected to what had happened half a world away. In northern Pennsylvania, the Kamchatka seismic waves appear to have done something specific and mechanical to the rock. The sustained shaking from the entire Kamchatka sequence, not just the main shock, but the weeks of foreshocks and aftershocks that surrounded it, may have broken what Beausset describes as pore pressure seals in the rock. This concept is central to understanding how earthquakes can be triggered by distant events, so let me explain it carefully. The crust of the Earth is not a solid, uniform mass. It is riddled with tiny fractures, pores, and channels, many of which are saturated with water and other fluids that are under pressure. The pressure of those fluids matters enormously to the mechanical behavior of the rock above and around them. Fluid pressure acts against the normal stress that holds a fault closed, the force that keeps the 2 sides of a fracture pressed together and prevents them from slipping. When fluid pressure increases, it effectively reduces the frictional resistance that keeps a fault locked. It pushes the fault closer to its failure threshold, and when pressure decreases in the wrong place, it can allow stress to redistribute in ways that bring other parts of the rock system closer to failure. Pore pressure seals are essentially natural plugs, zones in the rock where fluid pressure is compartmentalized, held in place by impermeable barriers. When those seals are intact, the pressurized fluid stays where it is, and the mechanical system remains stable. When those seals are broken by anything that shakes or stresses the rock sufficiently, the fluid can move, pressure can redistribute, and the stability of the entire system can change. What Beausset is proposing is that the seismic waves from Kamchatka arriving in northern Pennsylvania after traveling thousands of miles through the Earth were powerful enough and sustained enough to break those seals. The pore pressure was released, the fluid moved, and the rock, which had been sitting just below its failure threshold, began to slip in a swarm of tiny earthquakes. The swarm initiated, and then, critically, it developed its own internal dynamics and kept going for weeks. The Kamchatka earthquake did not just cause a single burst of seismicity in Pennsylvania. It appears to have fundamentally reorganized the state of stress in the rock, setting off a process that continued long after the seismic waves from Russia had faded into silence. In New Jersey, the mechanism appears to have been somewhat different. New Jersey is still experiencing aftershocks from the 2024 magnitude 4. 8. Tewksbury earthquake, a moderate event that was felt across the entire northeastern United States, and that reminded millions of people in the region that the ground beneath the densely populated New York metropolitan area is not as geologically inert as they had assumed. Aftershock sequences from moderate earthquakes typically decay according to a predictable mathematical pattern. They become less frequent over time, at a rate that seismologists can model fairly precisely. What Beausset found in New Jersey was a deviation from that pattern. After Kamchatka, the rate of aftershocks from the 2024 Tewksbury earthquake increased. The Kamchatka seismicity appears to have given the New Jersey fault system a nudge, enough to accelerate the release of stress that was already accumulating in the aftermath of the 2024 event. The aftershock sequence, which had been following its expected decay curve, picked up. More small earthquakes appeared in the weeks following Kamchatka than the model predicted should have been there. In Massachusetts, the story is still being analyzed. Bosé and his colleagues are refining their estimates of the earthquake locations in all three states, trying to determine whether there are patterns of migration in the swarms, whether the earthquakes moved through the rock over time in ways that could reveal the specific mechanism driving them. Migration patterns in earthquake swarms are often associated with fluid movement or slow fault slip, and identifying them could help distinguish between different hypotheses about what the Kamchatka waves actually did to the rock. Right now, the research is ongoing, and Bosé is careful to say that they are still working to separate the direct effects of the seismic waves from the secondary processes that those waves may have set in motion. But the connection to Kamchatka is clear enough that he and his colleagues are presenting it at the Seismological Society's annual meeting with confidence. What makes this finding genuinely important, beyond its immediate strangeness, beyond the almost cinematic quality of an earthquake in Russia shaking the ground in Pennsylvania, is what it suggests about stable continental regions and why they have earthquakes at all. The standard model of seismicity is built on plate tectonics. Earthquakes happen at plate boundaries because that is where the stress accumulates. The plates move, they collide or grind or pull apart, and the friction and pressure at their edges builds until something slips. In that model, the interior of a plate, old, cold, stable crust far from any boundary, should be quiet. The stress is not there. The forces are not there. And yet, it is not quiet. Eastern North America has been producing earthquakes for as long as human beings have been recording them. And before that, the geological record shows evidence of large prehistoric earthquakes in the region. Events called intraplate earthquakes, whose causes remain one of the genuinely unsolved problems in seismology. Bosé's hypothesis is part of a broader framework that a growing number of seismologists find compelling. Stable continental regions may be seismically active not primarily because of local tectonic stress, but because they are sensitive, unusually sensitive, to small perturbations that arrive from outside. The crust there is old and pressurized and intact in ways that younger, more active crust is not. It is like a structure that has been loaded with stress for a very long time without releasing it, and that has developed internal compartments of pressurized fluid held back by seals that are just barely holding. When a large seismic wave passes through, it does not need to provide enormous energy to disturb that system. It just needs to provide enough energy to tip something that was already close to tipping. And the seismic waves from a magnitude 8 earthquake, even attenuated by thousands of miles of travel, are not trivial. They are real, measurable forces arriving in the rock from a specific direction, carrying specific frequencies that interact with the existing structure of the crust in ways that are still not fully understood. Bosé said it directly in his presentation. The triggering power of the seismic waves radiated by large earthquakes is really not well understood. That is a remarkable statement coming from a seismologist presenting peer-reviewed research in 2026. It means that after decades of studying earthquakes, after instrumenting the crust of the Earth with thousands of seismometers, after developing sophisticated models of fault mechanics and fluid flow and stress transfer, we still do not have a clear quantitative framework for predicting when a distant earthquake will trigger seismicity somewhere far away. We know it happens. Kamchatka is not the first example. Large earthquakes have triggered distant seismicity in geysers, in volcanic systems and fault zones around the world. But the rules governing when it happens, what the threshold is, which locations are vulnerable and which are not, remain elusive. That uncertainty matters for reasons that go beyond scientific curiosity. It matters for how we think about seismic risk in places like Pennsylvania and New Jersey and Massachusetts, places that are home to tens of millions of people, that contain some of the oldest infrastructure in the United States, that sit above a patchwork of old faults and pressurized rock systems whose behavior is now revealed to be responsive to events happening on the other side of the planet. The 2024 Tewksbury earthquake in New Jersey was a wake-up call for many people in the northeastern United States. A magnitude 4. 8. It was not a catastrophic event, but it was large enough to be felt from New York City to Boston. Large enough to cause some structural damage in buildings not designed with seismic resistance in mind, and large enough to remind engineers and emergency managers that the Northeast is not immune to earthquake hazard. Now, the research from Kamchatka suggests that the fault system responsible for that earthquake is still active and still capable of being nudged by external forces, including forces that originate thousands of miles away. There is something else about the Kamchatka earthquake's effects that did not make many headlines at the time, but that deserves mention here. When the seismic waves from the July 2025 rupture arrived in the United States, they were not just felt underground. The earthquake was large enough that its seismic waves set geysers erupting more frequently, disturbed water wells, and in some locations produced measurable changes in groundwater levels. This is a known phenomenon. Very large earthquakes can temporarily alter the hydrology of regions far from the epicenter, changing the flow rates of springs, triggering activity in geothermal systems, and causing measurable fluctuations in aquifer pressure. These effects are real, and they are connected to the same pore pressure physics that Bosé is studying in the context of triggered seismicity. The fluid systems of the crust, the water-saturated fractures and pores that permeate the rock for kilometers below the surface, are not isolated from the seismic environment. They respond to seismic waves, and when they respond, they sometimes move the rock. The 7 volcanoes that erupted on Kamchatka after the earthquake are part of the same story. Earthquake-volcano interactions are real and documented, though the specific mechanisms are still debated. In the case of the Kamchatka earthquake, the timing is hard to dismiss. 7 volcanoes erupting simultaneously after one of the largest seismic events in modern history, in a region where such simultaneous multi-volcano activity had not been seen in 3 centuries. Krasheninnikov erupting for the first time in human recorded history 4 days after the rupture, with no seismicity buildup in the days immediately before the eruption. These things are connected. The earthquake did not just move the surface, it moved the interior of the earth, and the interior responded. All of this together, the triggered seismicity in Pennsylvania and New Jersey and Massachusetts, the groundwater changes, the volcanic activity, paints a picture of the planet as a far more interconnected system than the standard tectonic model suggests. We tend to think of earthquakes as local events. Something happens in one place, on one fault, and the consequences radiate outward in proportion to distance. The further you are, the less you feel it. That is largely true for the immediate effects of any earthquake, the shaking, the damage, the tsunami. But it is not true for the secondary effects, the subtle reorganizations of stress and fluid pressure and volcanic plumbing that propagate through the interconnected systems of the Earth's crust and mantle. Those effects can travel far and arrive in places where no one expects them, triggering responses that then develop their own momentum and last for weeks or months. Eric Bosé, speaking at the Seismological Society meeting, framed his finding as part of a broader question about stable continental regions. He is trying to understand why places like eastern North America have earthquakes at all. The Kamchatka finding is not the final answer to that question. But it suggests that at least some of the seismicity in those regions, those puzzling tremors in old supposedly quiet crust, may not be local at all. They may be echoes. Distant reverberations of enormous events happening far away, arriving in rock that is primed to respond because it has been accumulating stress without releasing it for decades or centuries, and that is shot through with pressurized fluid systems, waiting for a nudge that is large enough to break the seals. That is a genuinely different way of thinking about earthquake risk. It means that the seismic hazard of a place like Pennsylvania or New Jersey is not determined solely by what is happening on the local faults beneath those states. It is also shaped, however slightly, by what is happening at subduction zones on the other side of the planet. 7:58 a.m. 4 tars, 19/2026. Queen. He, next time, a magnitude 8 or 9 earthquake tears open a subduction zone somewhere in the Pacific or the Indian Ocean. Someone, somewhere in the stable interior of North America, may feel a small tremor a few hours or days later and not know why. They will not feel the connection. The ground under their feet will shake in a way that seems to have no cause, in a place where earthquakes are not supposed to happen, and most people will not know that the cause is half a world away, in a rupture that happened on the other side of the ocean. The Kamchatka earthquake of July 2025 did not destroy Pennsylvania. It did not crack houses in New Jersey or crumble walls in Massachusetts. The triggered earthquakes were tiny, magnitude 2, mostly unfelt, entirely harmless in any immediate sense. But what they reveal is something important about the nature of the planet we live on and our understanding of the forces that move it. The Earth is one system. Its faults are not isolated. Its fluid systems are not contained. Its seismicity is not purely local. A rupture large enough, on a fault well positioned to radiate energy toward a sensitive region, can reach across an entire hemisphere and wake up the ground beneath people who have no idea anything unusual happened. 9 months later, a scientist sitting at a computer at the Lamont Doherty Earth Observatory in New York, looking through a catalog of tiny earthquakes in Pennsylvania, finds the fingerprint of Kamchatka hiding in the data. Hour-long bursts, month-long swarms, the slow rearrangement of pore pressure in rock that had been stable for years, and realizes that the ground here is connected to the ground there in ways that our models are only beginning to capture. That is the story. Not dramatic in the way that a tsunami is dramatic, not visible in the way that a crumbled building is visible, but real and quietly stunning in the way that the best science always is. It shows you that the world is larger and more interconnected and more surprising than you thought it was before you knew this thing that you now know. That is everything for today. If this kind of story, real science, real events told honestly and with the depth they deserve, is what brought you here, please subscribe, because this channel will keep bringing you exactly that. I will see you in the next one. 8:12 a.m., 4/19/2026. Queen. It opens with 3 real people. Siddhi Rohayati, the street food vendor, Budi Nurgianto Internati, Martin Mandagi, and Betong, before a single number is given. This is a deliberate choice. Most earthquake coverage starts with the magnitude. This script starts with the morning, because the earthquake happened to people who were having a morning, and that is the most honest way to enter the story. The 70-year-old woman who died is named and treated with dignity throughout, not as a death toll, but as a person. Her name is not publicly available in the reporting, which means the script refers to her by who she was and what happened to her, not by a number. The tectonic explanation of the Molucca Sea, the arc-arc collision, the plate being consumed from both sides simultaneously, is genuinely unusual and is explained in plain language that most geology content never manages. It gives viewers something to remember and share. The section on why earthquake deaths are never purely geological, that they happen at the intersection of geology and building quality and economic circumstance, is the moral center of the script, and it is the kind of honest perspective that builds a loyal audience over time.